A warm welcome to everyone. I am Arun TN. In this presentation, we are going to see about population dynamics. We are going to see population dynamics in the following categories: first, definition and history and logistic function and intrinsic rate of increase and epidemiology and evolutionary game theory. First, definition. Population dynamics is a type of mathematics used to model and study the size and age composition of populations as dynamical systems. Population dynamics is the study of how and why populations change in size and structure over time. Important factors in population dynamics includes rates of reproduction, death and migration. This is the percent of total population. Now, history. Population dynamics has traditionally been the dominant branch of mathematical biology, which has a history of more than 220 years. Although over the last century, the scope of mathematical biology has greatly expanded. The beginning of population dynamics is widely regarded as work of Malthus, formatted as the Malthusian growth model. According to Malthus, assuming the conditions remain constant, a population will grow exponentially. This principle provided the basis for the subsequent predictive theories such as demographic studies such as the work of Benjamin Gorbdes and Pierre Francois's work in the early 19th century, who refined and adjusted the Malthusian demographic model. Now, logistic function. Simplified population models usually start with 4 key variables, including death, birth, migration, and immigration. Mathematical models used to calculate changes in population, demographics, and evolution hold the assumption of no external influences. Model can be more mathematically complex where several competing hypotheses are simultaneously confronted with the data. Now we can look at the formula. For example, in a closed system where immigration and emigration does not take place, the rate of change in the number of individuals in a population can be described as dn divided by dt is equal to b minus d is equal to bn minus dn is equal to b minus d in multiple by n, where n is the total number of individuals in the specific experimental population being studied, b is the number of births, d is the number of deaths per individual in a particular experiment or model. Now we look at the algebraic symbols. The algebraic symbols b, d and r stands for rates of birth, death and rate of change per individual in the general population. The intrinsic rate of increase. This formula can be read as the rate of change in the population, that is dn divided by dt is equal to births minus deaths, that is b minus d. This is the Malthus population principle. Using these techniques, Malthus population principle of growth was later transformed into a mathematical model known as logistic equation. dn divided by dt is equal to an multiple to 1 minus n divided by k, where n is the biomass density, a is the maximum per capita rate of change, and k is carrying capacity of the population. Intrinsic rate of increase. The rate at which the population increases in size if there are no density dependent forces regulating the population is known as intrinsic rate of increase. It is dn divided by dt is equal to rn, where the derivative dn divided by dt is the rate of increase of the population, n is the population size, and r is the intrinsic rate of increase. The concept is commonly used in insect population ecology or management to determine how environmental factors affect the rate at which pest populations increase. See also exponential population growth and logistic population growth. Epidemiology. Population dynamics overlap with another active area of research in mathematical biology. Mathematical epidemiology is study of infectious disease affecting populations. Various models of viral spread have been proposed and analyzed and provide important results that may be applied to health policy decisions. Evolutionary game theory. Evolution game theory was first developed by Ronald Fisher in his 1930 article The Genetic Theory of Natural Selection. In 1973, John Maynard Smith formalized a central concept, the evolutionary stable strategy. Population dynamics has been used in several control theory applications. Evolutionary game theory can be used in different industrial and other contexts. Industrially, it is mostly used in multiple input, multiple output. In short form, MIMO systems, although it can be adapted for use in single input, single output systems. Some other examples of applications are military campaigns, water distribution, dispatch of distributed generators, lab experiments, transport problems, communication problems, and among others. This is a chart of population dynamics. It can be classified into housing, transportation, environment, urban growth and change, education, labor force, and health. And thank you for listening.